Hello, class. Today we'll be learning about the history of science and how the observations and experimentations of early scientists helped pave the road for our present-day understanding of the world. Albert Einstein is one of these scientists who helped shape our modern-day ideas about the scientific world around us. But before we talk about Einstein, we need to talk about some scientific achievements throughout the 19th century. Believe it or not, many of the things we use without even thinking about weren't even ideas until the 19th century. Around this time, numerous life-changing ideas came about through experimentation. People of this time began to understand concepts of optics, electricity, radioactivity, magnetism, acoustics, gases, and kinetics. These accomplishments helped set the stage for the beginning of modern-day science. One noteworthy scientist of this time was Josiah Gibbs. Gibbs was an American scientist who was unbelievably smart. He was a chemist, physicist, and mathematician who applied his scientific knowledge to study thermodynamics. Thermodynamics is just a fancy word that is used to describe the flow of heat and energy between objects. Gibbs didn't know it at the time, but his work would be the start of modern-day science as we know it. Some of Gibbs' most important experiments were his studies of thermodynamics on the atomic level. In 1875 through 1878, he published papers on the equilibrium of heterogeneous substances, which proves that heat and energy transfer didn't just apply at the macroscopic level, with things people can see and understand like the heat from a steam engine, but also at the atomic level. This was groundbreaking information. So much so that it began an entire new era of science. This new time period would be referred to as the quantum age. The quantum age refers to the period of time where science, more specifically physics, switched from studying things at the macroscopic level to the microscopic level. This is where Albert Einstein comes into play. In the early 1900s, Albert Einstein used the current understanding of science and began taking it to the next level. With a series of papers in 1905, he explained the nature of light, he proved the existence of the atom, and perplexed the world with his theory of relativity. Despite some confusion from the public, these revelations would change the thinking of the world forever. Einstein's work on the theory of relativity led to the famous equation E=mc², which helps explain the relationship between energy and mass and also explains that the speed of light is constant. The equation states that energy of an object is equal to the mass of the object times the speed of light squared. Essentially, matter has a lot of potential energy, we just aren't efficient at using it. In 1907, Einstein observed a worker fall off a ladder. Little did that worker know, but he may have participated in an experiment of a lifetime. Einstein uses this observation to begin to think about gravity. Through his observation, he begins to view gravity not as a force, but as a result of bending space and time. His thoughts lead him to start thinking about the universe as a whole, not just about the processes on Earth. To make things even more complex, in 1917, Einstein applied his understanding of relativity to the cosmos in a paper called Cosmological Considerations on the General Theory of Relativity. In short, the paper stated that space and time were not absolute, but relative to the observer, in case the general public wasn't already confused enough. The common person, or the common scientist for that matter, couldn't even begin to understand Einstein's theory until Bertrand Russell, a mathematician and philosopher, successfully simplified and publicized the idea with ABCs of relativity. The two models he gave the public were of a moving train and of sound waves. The first example was to picture a 100-yard long train moving at 60% the speed of light. To an outside observer, the train would only appear to be 80 yards long and the passengers' voices would be slurred. However, to the passengers, nothing would be different. The observed time on the train would also only be about 4/5 of the time observed outside the train. In the second example, a person hears annoying music and moves further from the sound so they can no longer hear the sound. Nothing about the sound has changed, but the person's position relative to the sound has changed. Through the use of analogies that the average person could understand, these complex ideas soon became understandable for the general public.